I will start recording, and I will formally welcome Petro to start her presentation. Thank you.
Thank you for the introduction. Good morning, everyone. I'm going to switch off my camera because it's a little bit distracting. You can just listen to my voice. Yes, as was said in the introduction, my name is Petro. I did a master's by coursework and dissertation under the National Astrophysics and Space Science program. And I worked under the supervision of Dr. Nick Erasmus and Professor Matthew Bashedi. And for my dissertation, we looked at the characterization of small, close approaching near-Earth asteroids. And that is what I will be presenting today. So going to the basics, going to the basics, I'm sure we all know that in between the orbits of Mars and Jupiter, you get the asteroid belt. Now, asteroids in the asteroid belt get heated by the sun, and as they re-radiate that heat away, there's a small thrust that causes them to move in semi-major axis, meaning they move closer to the sun and away from the sun. And because they move in semi-major axis, they move into regions where they experience a resonant force with the larger planets like Jupiter and Saturn. And that resonant force then kicks them into orbits that come near or cross the Earth's orbit. And these asteroids are known as the near-Earth asteroids. The near-Earth asteroid population is thought to be in a steady state, which means the amount of asteroids going into the region is similar to the amount going out of the region. And by going into the region is exactly what I just explained. They're constantly being replenished with asteroids from the main belt, and going out of the region means they escape the solar system or they collide with the sun or a nearby planet. So this animation, I quite like it because it shows the orbits of the near-Earth asteroids in blue, and the orbit of the Earth is shown in white or light gray, and all of the main belt asteroids is shown in orange. And here you can see how close they are to the Earth's orbit. And this is just a nice animation that showed. But why do we care about near-Earth asteroids? What makes them so interesting, and why would we want to study them? I'm going to explain a few reasons why they are interesting and why they are beneficial to study. But I'm sure the reason most people know about near-Earth asteroids is not because they are beneficial, but because they're destructive. But let's first start with why they are interesting objects. And the first reason is because they can help us with the formation, help us understand the formation of the solar system. Asteroids are thought to be the remnants of the solar system formation. And if we understand the compositional distribution of asteroids in the main belt, then we can get an idea and it can help the models to understand how the solar system came to be. For example, if there are more, I'm sure if someone is unmuted. For example, if the outer region of the main belt contains more carbon-based asteroids and the inner region of the main belt contains more solid rock or silicate-based asteroids, what does that mean? What happened in the history of the formation of the solar system? Or what if all of them are a mess? Like there's a lot of compositions all over the main belt. What happened to what happened when the planets formed? Maybe they formed at one location and they moved, and that caused everything to shuffle around. Main belt asteroids are quite far away, and some of them can be small and dark, so they're not easy to observe from the Earth. And that is when near-Earth asteroids come in, because they just come to us. So even the smaller ones, even the darker ones, can easily be observed from the Earth. And since near-Earth asteroids basically come from the main belt, if we can understand the compositional distribution of the near-Earth asteroids, we can basically extrapolate that back to the main belt asteroids. So it's one of the reasons why they're interesting. It was not the focus of the study, but I just thought it would be interesting to share. The other reason why they're nice to study is because we can go visit them with spacecraft. The first reason is to do asteroid mining, which is another topic of discussion. But more interesting reason is for scientific purposes. And we actually have a recent example where the OSIRIS-REx spacecraft visited asteroid Bennu, which is about 500 meters in diameter, and it is a near-Earth asteroid. And last year, on the 20th of October, the spacecraft successfully collected a sample from the asteroid. And it is currently on its way back to the Earth. I think the most popular reason why people are interested in near-Earth asteroids is because of their impact risk. And because of their close proximity to the Earth, near-Earth asteroids can affect life on the Earth, both positively and negatively. And by positively, I mean back millions of years ago, when the Earth was still forming, there are theories that suggest that near-Earth asteroids and near-Earth comets delivered ingredients like carbon and water to the Earth that could have initiated life on Earth. But the reason, the most popular understanding of near-Earth asteroids is that they are destructive, and there's more theories that suggest that an asteroid of a few kilometers even destroyed many of the early life forms. Asteroids of this size, of a few kilometers in diameter, are only supposed to impact the Earth once every few million years, and most of them are already known. But the smaller asteroids, those of a few tens or a few hundreds of meters in diameter, statistically are supposed to impact the Earth more often because there are more of them, and most of them have not been discovered yet. A recent example of an impact by a small asteroid was in 2013 with the Characterization meteor event, and this was caused by only a 20-meter asteroid that exploded in the atmosphere. Asteroids of this size is only supposed to impact the Earth. Is someone unmuted? Asteroids of this size is only supposed to impact the Earth once every few hundred years. So, and asteroids of this size, most of them have not been discovered yet. As of yesterday, there are more than 26,000 near-Earth asteroids already discovered, and this number is increasing by about 6 or 7 per day. About 80% of these are considered small, which I characterized in my dissertation as those with a diameter less than 300 meters, and the remaining 20% of them are large with diameters greater than 300 meters. Even though the discovery rates have increased a lot in recent years, the characterization of near-Earth asteroids are still behind the discovery rate. In the past, most studies have focused on characterizing large asteroids because they are easy to observe from the Earth. They are usually bright and they don't move very quickly, and you can observe them even when they are far away from the Earth. But small asteroids, on the other hand, you can only observe them when they act or near their close approach to the Earth. So they're only observable usually for a few days or a few weeks, and then they move away from the Earth, and you won't be able to observe them for many months and mostly many years, which means it's not easy to characterize them. In the last 5 to 10 years, the characterization of small NEAs have increased a lot, but the characteristics of the small NEA population can still be better refined. And that is also why we decided to focus on them for this study and observe the small NEAs, or focus on the small NEAs for this study, and to obtain the general properties of the NEA population, of our small NEA population. So how we did this was to look at NEAs, to observe NEAs with the SAAO 40-inch telescope and the Sutherland high-speed optical camera, or SHOP. And I've included the specifications for anyone who's interested, but what's important is the field of view and that there are Sloan filters available. So overall, we observed 14 small NEAs and 6 large NEAs, and we use exposures between 5 and 30 seconds. Near-Earth asteroids generally move very quickly through the sky. They have very fast sky rates. So if your exposure time is too long, then the object will be streaked if your exposures are too long. So that's why we kept the exposure times short. And then also we used something called non-sidereal observations. Generally, when you observe an asteroid and you have a large field of view, you would keep the field the same and let the asteroid move through the field of view. But because the field of view of SHOP on the 40-inch is quite small, and these asteroids were moving very quickly, we decided to rather track the asteroid. So if we kept the field the same, the asteroid would move through the field of view in a matter of minutes, sometimes seconds. So instead of constantly moving the telescope, we just adjusted the tracking rates of the telescope. So it would track on the asteroid and the stars would move in and out of the field of view. And then also for the signs that we wanted to do, we used the RG and I filters, and we cycled through them as well. So this animation shows some of the observations, and I've tried to highlight where the asteroid is. It's usually near the center, and you can see that the asteroids, the stars are moving in and out of the field of view. So now that we have this photometric data, the next thing that we did was to get the light curves. So here is an example of just a couple of the targets and their light curves, which is basically just the time against the apparent magnitude. And as you can see, they all have different light curves depending on how they reflect the light and also the shape of the asteroid. So using these light curves, we basically wanted to look at 2 properties. It was the rotation period and the taxonomy. From the taxonomy, you can then infer the composition. So let me first introduce rotation period. The rotation period is basically just the time it takes for the asteroid to rotate once on its axis, or the time it takes for it to return back to its original position. Half a rotation period is basically the same as 1 light curve period, so an increase and a decrease of light. So the rotation period is basically twice the light curve period. Asteroids come in different shapes and sizes, and they also reflect light differently. Some asteroids, like this one, which is asteroid Bennu, is more spherical, which means its light curve would be relatively flat, but other asteroids like this one, like Eros, is more elongated, so it would have a larger amplitude as it reflects more and less light from the sun. Other factors that can influence the light curve of an asteroid is some of them are tumbling. Think about throwing a brick through the air. So it doesn't rotate just on one axis, but it rotates around more than one axis. And some asteroids can even have a companion. And all of this will affect how the light curve looks, and also, So we basically calculated the light curve or determined the rotation period for each of the targets. And here is I'm just showing two examples. I first formed a densely sampled light curve by shifting the G and the I data to match R. I got the Lomskal periodogram and extracted the light curve period out of that, multiplied it by 2 to get the rotation period, and at the bottom it's shown as just the phase light curve. So the data was just folded at the rotation period, so you can actually see the rotation. And what I then basically did was just to compare the rotation periods that I got to the rotation periods of known asteroids, which is shown in this figure from Warner et al., which is basically just the diameter against the period or the frequency of many different near-Earth asteroids and main-belt asteroids. And a notable feature is here, which is called the 2.2-hour spin barrier, which basically it just comes from the assumption that most asteroids are rubble piles, and if they spin faster than 2.2 hours, they will fly apart. But there are asteroids that exist that spin faster than 2.2 hours, and most of them are quite small as well. And 3 of the targets in our study fell into this region as well. And what it basically just means is they're probably not rubble piles, but they're solid pieces of rock. So even if they spin faster than 2.2 hours, they won't fly apart. And then the second property that we wanted to look at was the taxonomy. So asteroids don't generate their own light, they only reflect sunlight. So you can get their reflectance spectra and not just normal spectra. And depending on this spectra, they're divided into different taxonomic types. This key chart basically shows the average reflectance spectra of each taxonomic type. And from this reflectance spectra and taxonomy, you can infer the composition. For example, the S-complex asteroids are more stony or silicate-based, and the C-complex asteroids are, they're usually darker and they're more carbon-based. So using this then, it's not easy to, it's not impossible, but it's not easy to perform spectroscopy on faint, fast-moving objects. So instead of trying to obtain the spectra of these near-Earth asteroids, we instead got the photometry at a few key wavelengths and then used that to classify them and to determine its taxonomic type. So let me explain how we did that. So starting by just looking at the transmission curves of the GI and R filter on the 40-inch. If we then plot this average reflectance spectra of 6 different taxonomic types on top of that, and we only look at a few key wavelengths and we calculate the colors, then we can still differentiate between these different taxonomic types. The color is basically the slope, and you can see that all of the different taxonomic types have a different slope in this region and in this region. So to help with that, to be able to differentiate between the different taxonomic types, we used a machine learning approach. The reason why we only looked at 6 different taxonomic types is because near-Earth asteroids are mainly classified as these, and we can differentiate between them using only the colors G-R and R-I. So we on this in this figure is basically a color plot of G-R versus R-I, and the decision boundaries were generated using a machine learning algorithm. All of the data points shown here is the training data, and it was basically synthetic colors generated from classified spectra and also from the average reflected spectra. So here you can see how you can differentiate between the different taxonomic types just based on these 2 colors. Now we wanted to use this then to classify our targets. Let's say, for example, the color of a certain NEA fell here. Then you would say, oh, it's probably an S type. But what if its uncertainty reached into the X region and the C region and the Q region? Then how certain are we that it is actually an S type? And that is why we did what I demonstrated here. We calculated, or we generated 10,000 random colors with a Gaussian distribution within 1 sigma of the measured color uncertainties. And this is demonstrated here for 2 of the targets. And then we would just basically tally up all of the classifications in each taxonomy and calculate the probability. And if that probability was greater than 50% in a specific taxonomy, then I would assign it a distinct taxonomy. This figure is, again, the same decision boundaries, but now showing our classified targets. There are still, I think there's 4 of them that still remain, or 5 of them that still remain unclassified because none of the probabilities were greater than 50%. And even though they remain unclassified, through the probabilities that we calculated, we could at least exclude some of the taxonomies. So basically, we wanted to look more at the properties of our whole sample, because if we know the properties, in general, like the properties that most NEAs are, then that will help us understand, if there is an asteroid on its way to the Earth, what will its composition be, most probably. But our sample size was really small, and even though you can see that most of them are S or Q types, so they're mostly silicate-based asteroids, a more statistically correct way to get the compositional distribution of the sample is to calculate the fractional compositional distribution. And that was done by basically just adding up all of the probabilities in the S type, all of the probabilities in Q, and onwards. And that's what's shown here. My work is shown in color, and I compared it with 2 other studies as well. And you can see that it is comparable. For example, S type, within uncertainty, all of them are around 50%. So 50% of the NEAs are S type. And similar for the other taxonomic types. But an interesting result of the study was the fraction of S and Q type asteroids, which was almost 80%. And the reason why this was interesting is because it was similar to the fraction of meteorite falls that are due to ordinary chondrites. Now, what is an ordinary chondrite? It's basically just a type of rock, a type of meteorite. And when they study the spectra of this ordinary chondrite, it is similar to the spectra of a Q-type asteroid. So if 80% of meteorites are this type of rock, then we would expect that 80% or similar number of NEAs should be should be Q-type asteroids, but this is not the case. Therefore, it has been suggested that ordinary chondrites are not only just Q-type asteroids, but they're also due to S-type asteroids, and that these two types of asteroids actually have the same composition. And the results of our study agrees with this suggestion or assumption. Basically, Q-type asteroids are what they call unweathered, or they have a fresh exposed surface because of close encounters with the planet. And S-type asteroids are more weathered. So on the surface, they don't look exactly the same, but overall, they all have the same composition. And that is all. Thank you. Any questions?
Petro, I see there's a question from Gideon in the chat. I don't know if you want to read that.
I see, yes. So the question is, do we know what the general content of these kinds of asteroids are in terms of minerals or metals that are considered valuable or useful on the Earth? I think we have a general idea of what they are made of, or what most of them are made of. The majority of near-Earth asteroids are silicate-based, so they're just stony, like just a rock, basically. And then they are also carbon-based. I guess I'm not sure about how useful or valuable it will be on Earth. I guess carbon can be valuable. I mean, there's many theories that suggest that there are asteroids that have very expensive minerals and elements, and that's why they want to do asteroid mining. But I'm not, I'm not exactly sure about all of that. Okay, Patricia is asking, how do asteroids get weathered? Basically just what I like to call, they just live out there with other asteroids. Basically micrometeorite impacts, I think solar rays or something like that as well. They impact with they impact with each other, and the surface changes.
Hey, Petro, it's Vanessa here. Can I go next?
Yes,
Yes.
yes, please.
Cool. Thanks for a great talk. I wanted to ask, you know, at the beginning you said that the asteroid orbits change because of the variations of solar irradiation. Is that also what makes them rotate?
I think it has something to do with that, yes. I'm not exactly sure about the specifics. There's something called the Yarkovsky effect. It has an influence, yes, but I wouldn't say it's the only reason.
So they may also just, you know, begin their lives rotating, as lots of other things in the solar system, I guess.
Possibly, and also from colliding basically with the other asteroids.
Thank you.
Okay.
Petro, if I can add, Vanessa, they can the Yarkovsky can speed or slow down the rotation. That can happen. So it can evolve the rotation period.
Great, thanks.
I see Moses has another question. Is there a possibility of doing this with narrower filters? Will that make a big difference to the characterization? I'm not sure about narrower filters, but definitely more filters will be useful, so that you can use more colors, and you can even approximate the spectra just by getting multiple measurements. And I don't know if it will make a big difference to the characterization, but it will definitely improve it.
Can I just share my screen to show you what
Any other question? Okay. There is one question from Sriram. Are there extraplanar asteroid? If yes, do we know their origins?
What do you mean with extraplanar?
Like outside of the initial protoplanetary disk during star formation.
I think high inclinations or funny eccentricities.
Yeah, they don't all rotate within the plane of the. I mean, they don't all orbit within the plane of the solar system. There are also asteroids coming from outside of our solar system, or comets.
Okay, thanks.
I guess there are no more questions.
Any other question, please? No? Okay. If not, then we can now thank Petro for a very nice and introductory talk. Thank you, Petro.
Thank you.
And thanks everyone for joining us. Bye-bye. Have a nice day.
Thank you. Thanks very much. Bye-bye.